So, my name is Richard Steenbergen, and we're here today, or not here today as the case may be, to talk about a practical guide to correctly troubleshooting with Traceroute. So, you have a problem on the internet. Something isn't behaving right, something isn't performing right. The number one go-to tool for network people is Traceroute. Basically, every operating system on the planet comes with a Traceroute tool of some kind, and there's lots of websites where you can run. There's lots of looking glasses. There's lots of public Traceroute tools. And there's a lot of visual Traceroute tools. There's things that try to make it really simple and easy and paint a picture for the end user. It seems like such a really easy, simple tool to use. I mean, all you do is type in an IP address and it shows you every router hop along the way and a latency measurement. And the naive assumption is that if you look at where the Traceroute stops or where the latency jumps up a lot, that's where the problem is. And turns out that tends not to be the case. Well, why is that? Modern networks are actually pretty well run. So the simple issues, routing loops, congestion, things that we used to see a lot in the past that were really easy to diagnose, those are pretty rare these days. So there's really few people that are skilled at interpreting Traceroute out there. And I know it looks really simple and easy to use, and it tends to give most people the impression that they're qualified to interpret it and locate the fault. But in reality, most NOCs, and in my experience, even most junior to mid-level IP engineers, aren't actually qualified to interpret a complex traceroute. It's a very, very difficult thing. It's a lot of subtle things that you have to know about to do it right. So what ends up happening is you end up with this huge number of bogus traceroute complaints. Anyone who's ever worked a NOC or looked at tickets that come in from end users gets traceroute tickets, and there'll be screenshots in a Word document in a zip file of someone's traceRT.exe window, and they'll say, hey, my game isn't working, my this isn't working, help me fix it. And it turns out that it's really very difficult to get anything looked at if you have a real problem because there's so many false complaints out there. So the goal of this talk is to kind of improve everyone's knowledge of how to interpret Traceroute and hopefully get the false issues down a lot. So here's an example Traceroute output. And the implementations really vary a lot, but at a basic level, every Traceroute looks a little bit something like this. So there's a hop number. There's the router IP that you're showing. So that's going to show you the IP address, and then it's going to do a reverse lookup and figure out the DNS. And then there's going to be some latency measurement. So in this example, each router hop has 3 separate latency probes, and it does the 3 probes and then iterates to the next hop. But here's what this looks like at a packet level. So the first thing we do is we launch a probe packet towards the destination. We set our TTL, our time to live, value at 1. And every router that forwards the packet, by definition of how routing works, will decrement the TTL by 1. And then when the TTL hits 0, the router drops the packet and it returns an ICMP TTL exceed is the name of the protocol type. And it sends it back to the source that sent the packet. So that source receives that ICMP message, and now it calculates a time difference. So it says, I sent this one out at this microseconds, and I received the reply at this microseconds, and here's what we think the total time difference is. And it displays that value as a hop and a probe. So then we go back to step 1. Now we increment. So we launch with a TTL of 2. So as it goes further along, every router that goes towards the destination will get exposed to this packet, will drop it, will send an ICMP back, and eventually when you hit the host, you return an ICMP unreachable. So that'll either be a network unreachable or a destination unreachable that you've hit a port that isn't listened to. And when the source receives that ICMP unreachable, then the traceroute ends. It knows that it's complete. So most implementations send multiple probes per hop. So for example, the vast majority of tools that are out there send 3 separate probes. So for every hop, for every TTL increment, you're looking at 3 totally separate measurements. And every probe packet is completely unique. So it's its own independent trial. So each probe packet uses some kind of a unique key to identify itself. So a lot of very common Unix implementations and router implementations are based on UDP, and they use incrementing ports. So they'll set source ports and destination ports in a way that it can identify itself when it comes all the way back. But there's other examples of tools that use ICMP. So for example, Windows Traceroute defaults to ICMP. There's a lot of tools out there that'll let you use TCP and other things to try and work around firewalls and do other kinds of measurements. But like I said, every probe is a completely independent trial. So each packet may be forwarded down a completely different path. And this may be visible to the end user, or it may not be. So the latency calculation is really simple. Like I said, we take a timestamp of when we launch the probe, and we take a timestamp of when we get the ICMP packet back, and you subtract the difference, and there's your round trip time. So routers along the path don't actually do anything to the packet. They don't do anything other than, they're not involved in the time calculation, I should say. So they are involved in generating the ICMP, but they don't do any time processing. There's some implementations that will encode in the payload of the packet, they'll encode some like very accurate timestamp. But the reported latency that you're looking at is actually the sum of the total time taken to forward the packet to the router that dropped it, the time for the router to generate the ICMP response, and the time for the ICMP packet to reach the sender. So you're looking at a complete round trip to come all the way back, and that's what you're viewing. So let's take a little more look in more detail as to what hops you're actually seeing. So here we start with the probe packet entering router 1. The TTL hits 0 and the packet is dropped. So router 1 generates its ICMP TTL exceed and it sends it back to source. And it sets a source address based on, so what it sets as the source address for the ICMP message that it sends is going to be what shows up in your traceroute. So by convention, what it does is it sets the source to the ingress interface. So if we look at the traceroute above, we're going to see 172.162.1. So we're going to see that ingress interface coming into router 1, and we're going to see the ingress interface coming into router 2. What you're not going to see is the egress interface or the egress path. You know nothing about that. So the return path coming back to you is effectively invisible. So all those 192.168 addresses on those return interfaces, you don't see, you have no visibility into. So a little random factoid about Traceroute, if you actually go read the RFCs that should govern how all this works, Traceroute is actually non-standard. So RFC 1812 says that ICMP source must be generated from the egress interface. And if this were to be obeyed, Traceroute would effectively be non-functional. But through convention, everyone has managed to implement this correctly so that Traceroute works. So now we're going to talk about how do we interpret DNS in Traceroute. So you don't read a traceroute by IP alone. It's really painful if you run across a network who doesn't provide any reverse DNS, but most operators are nice enough to do that for you. And correctly interpreting the DNS is pretty much one of the most important things about successfully reading the traceroute. So the things that you can gather from DNS, you're going to get your geographic location. So you're going to know something about where the router is. You're going to learn something about the interface types and capacities. You're going to learn something about the router types and roles, and you're going to learn something about where the network boundaries are, where the relationships are between providers. So let's look at location data. So knowing the geographic location is pretty much the most important thing to understanding what's going on. So it'll help you figure out if there's some kind of incorrect or suboptimal routing. If you're bouncing from New York to London to come back to Chicago, for example, that's not going to be ideal by any stretch of the imagination. It's going to help you understand where the network interconnections are, and even if you don't know there's a problem, you'll be able to figure out if the high latency is justified or not. So the most common used locations are location identifiers are the IATA airport codes, the CLI codes, CLI codes, some abbreviation of the city name, and then sometimes you just have to guess because people make up random things. So let's talk about the airport code. So there is an international standard body called the IATA that publishes airport codes. And this works really well because it covers pretty much every large metropolitan city region in the world has an airport in it. And so there's an airport code. So you end up with, this works really well for people who have a large number of fewer POPs. So for example, if you're a global backbone provider with capacity in major cities. So you're in London, you're in Frankfurt, you're in Paris. It works really well. If you are someone with a large number of locations, so imagine if you're a telco and you have thousands and thousands of POPs and you cover all these little small cities, it tends not to work very well for that. So some examples: SDQ, Santo Domingo. Well, you can tell how old this slide was when I wrote it. This was the original NANOG in Santo Domingo. San Jose, California is SJC. So there's pretty much a major airport code everywhere. Sometimes you'll see this represented by the metropolitan area codes. So this happens when you've got multiple airports that service the same region. And sometimes this can be helpful and be more intuitive, and sometimes it can be a little less intuitive. So for example, New York City is serviced by 3 major airports. So you've got JFK out in Long Island, you've got LaGuardia, LGA, and you've got Newark over the border in New Jersey, EWR. So there is a code NYC that is used to represent all 3. So you might be perfectly within your rights to pick NYC as the name of your POP code to kind of cover the entire geographic region without having to nitpick over whether you're closer to LGA or JFK, and kind of improve communication. Another example is Northern Virginia is serviced by IAD. That's the Dulles, that's the closest airport. But you might also see DCA, that's the one in downtown DC, Reagan National. There's a metro code that covers all of those, WAS. But it also represents BWI, Baltimore, which is actually a pretty good distance away from Northern Virginia. So you can win or lose on these codes. Sometimes you see them used, and sometimes they can be a little more confusing, sometimes a little less. Silly codes are what's called the common language location identifier. So these are codes that are maintained and sold by Telecordia, and it's really for North American telcos. So here's an example of a code, and this identifies a particular CO or something along those lines. What you'll typically see in a non-telco role is you'll pull out just the city and state identifiers. So Houston, Texas might be HSTNTX, Ashburn, Virginia might be ASBNVA. NTT is probably the biggest notable user of this as global tier 1s go. But there's a well-defined standard for all North American cities. So every telco, everyone who has assets in the field that is managing large numbers of locations tends to follow this standard. Problem is, it's not an actual standard outside of North America. So like I said, NTT being an example of a major global provider that uses this, they made up their own that fit in the same format. So if you're in North America, there's a database you can look up, but if you're not, you pretty much have to guess. And then sometimes people just use arbitrary values. So here's an example of one where you might use an arbitrary value. Toronto, Ontario in Canada. The IATA airport code, so there's 2. There's YYZ, which is the big one, and YTC, which is the smaller airport downtown. But the metro code for both of those is YTO. And you could look at those and think that none of those are terribly convenient for an end user to know what the heck that means. So sometimes people will just use the code TOR. Typically this happens when you've got really good intentions. You're trying to make things readable for English users. But the problem is it doesn't follow a known standard. So sometimes these can be pretty difficult to reverse engineer what they actually meant when you actually go to read it. So here's a little table of the major US cities that you'll typically see pop up in Traceroute, because these are the primary interconnection hubs. This is where most traffic will be exchanged or routed, where the core routers will be located. So you can look at this for handy reference. And here's the same thing on the major global cities. These are the big locations that you'll often see traffic routed through. And here's the airport codes, the metro codes, the silly codes, and then some other codes that people will use. The next thing we look at is how do we interpret interface types. So most networks will be nice enough to put their interface information in DNS. And the real question is whether it's up to date or not. So if you've got a really well-run network, they have an automated tool and it generates automatic DNS. So if a router config gets moved to a new port, sometime like within 24 hours, it'll get pushed and updated and everything will be known. And there's some other networks that are shockingly bad at keeping their DNS up to date. So the larger or more telco-like they are, the more I tend to find that they're really, really bad at keeping them up to date. And I've seen some DNS pop up. It's like, wow, that company's been bankrupt for like 15 years. There's still a DNS entry for it. But assuming the DNS is up to date, this can really help you identify what type of interface, as well as the capacity and maybe even the make or model of the router. So here's an example of a level 3. This is quite old, but an example of a hop from level 3. So when you see XE-, you know that that's a Juniper 10 gig port. So you know by the slot naming that it has at least 12 slots, and there's at least 4 PIC slots for this to be a 10 gig on. So it's highly likely this is a Juniper MX960. It could be some other device. There's been a lot of different permutations of this out there since then, but it gives you an idea of what kind of device you're looking at. And if you start to look at the other side of the /30, things like that, or /31, you'll be able to figure out more details. So here's a little database of common naming conventions. So this shows you what it looks like in classic iOS, in iOS XR, which has a different naming scheme, and then Juniper convention, which is very different. And you can see kind of the basics for all of them. So now we're going to look at knowing the role of the router. So remember, every network is different, but they all generally have some kind of a naming convention. But just to be extra confusing, sometimes they don't always follow their own rules. So you can usually guess the context. So an example of a core router, CR, core router, core, BB for backbone, CCR for core, BBR for backbone router. Peering routers, you tend to see things that are named like BR, border router, border, edge, interconnection router, or peer. Those are some really common ones. Customer routers tend to have names like aggregation or customer, AR, or CAR, customer aggregation router, or HSA, high-speed access, or GW, gateway. These are some very common conventions that you see in a lot of the major backbones that are out there. So the reason you care is you want to be able to identify a network boundary. So the network boundaries matter because this is where the routing policy changes tend to occur. So for example, a different return path based on local pref. You might local pref a peer above a transit provider, or you might local pref a customer above a peer. In fact, you pretty much are almost always guaranteed to do that. So these tend to be the places where the routing changes because of that, or because the capacity or the routing is the most difficult. So any kind of a network border between two peers, you might be seeing peering congestion or transit congestion, or even customer congestion. So identifying the relationship, typically you want to figure out the 3 major relationships are, there's either a transit relationship, a peer relationship, or a customer relationship, and customer and transit being the inverse of each other. So one transit provider's the customer is a customer of a transit provider. They go back and forth. So many networks will try to indicate this in their DNS, and it's really helpful for knowing where that is. So clear names like network name.customer, or always landing customers on some kind of a router like name GW. Knowing where the customer demarc is, in my experience, tends to be the most important, because customers tend to be the ones who screw up their routing or screw up their network in some way. And you can usually pass the blame from the network provider onto the end network, and kind of have the person submitting the Traceroute ticket talk to the person who's better able to respond to the issue. So it's pretty easy to spot where the DNS changes. Here's an example where you're going along and hop 4 says global crossing. Wow, that's defunct. And hop 5 says Sprint. Another thing that you'll see pop up is when you see the remote party in the DNS name. So here you see hop 4 was clearly global crossing, and hop 5 is the Cogent side of a global crossing. And where you see that happen is where one side or the other provides the /30, and they get too lazy to go ask the other party, hey, what do you want your DNS to be? So they just set it to this convention. And a really easy way to look that up is to go to the other side of the /30. So here, if we, 107.90, the other side of that /30 would have been .89. So you go do a DNS lookup on that, and you can see that that's the other side of the global crossing interface. So you see that it came in PO2 and it went out 10 gig 2/3. Now we're going to talk about network latency. So there's three primary causes of network-induced latency that we care about. The first is serialization delay. So basically that's caused by the packetization of data. As we take data and break it up into little chunks, it has to be sent that way, and that causes serialization delay. Number two is queuing delay. So this is caused whenever the router or switch has to buffer the packet while waiting for an opportunity to transmit it. And the third is propagation delay. So this is pure distance related electromagnetic propagation. Light only moves so fast. So let's talk about serialization delay. So a packet moves through the network as an atomic unit. So you can't do something like transmit half a packet and finish it later. It would be dropped. It would be a bad packet. So generally speaking, nor can you start transmitting a packet until you've finished receiving it. There's some exceptions to this. There's some devices that do what's called cut-through switching. But this is pretty rare. The reason being it requires every network interface to be exactly the same. So you would have to have a 10 gig in and a 10 gig out to do that kind of a cut-through switch where it starts to transmit the packet before it's fully received. But generally speaking, every major device that you run into is what's called store and forward. So it actually waits until it gets the whole packet, does a lookup, and then sends it to its destination. So serialization is the process where the data is actually written onto the wire. So the faster an interface is, the quicker this process occurs. And the math is really simple. The delay is the packet size divided by the link speed. So here's an example where you send a 1500 byte packet over a 1 megabit link. So 1 megabit per second is 1,000 kilobits per second, is 125 kilobytes per second, which is 125,000 bytes per second. So if you do 1,500 bytes divided by 125,000 bytes, you end up with a total transmit time of 0.012 seconds, which is 12 milliseconds. Remember that networking uses the true SI definition. So when we say kilobit or kilobyte, we mean 1,000. We do not mean 1,024. That's a kibibyte, and that's only used in some applications on host devices. So remember, every single time a packet-aware device, every time you do a routing lookup or a switching lookup, you're adding a new serialization delay. Don't forget about layer 2 overhead in this. So when I said a 1,500 byte packet, that's what we think of at an IP layer. But here's what happens when you actually go to transmit it over the wire. So the preamble and the starter frame delimiter consumes 8 bytes of wire space. You have to put an Ethernet header on it, that's 14 bytes. You have to put our payload, and if for whatever reason our payload, if our IP packet was smaller than 46 bytes, Ethernet requires you to pad it to 46 bytes. Then you have to put a frame checksum, that's another 4 bytes, and then you have to have an interframe gap, and that's 12 bytes of wire time. So when you send a 1,500 byte IP packet, a really common IP packet, it actually consumes 1,538 bytes across the wire. And don't forget, there might be VLAN tags, there might be MPLS shims, these might be stacked multiple times, you might be inside of a tunnel, you might be inside of more things that are adding more overhead. But if you were to look at a pure simple Ethernet link, the actual serialization, instead of 12 milliseconds, it's 12.3 milliseconds because of the extra overhead that we've added doing the layer 2. So fortunately, this is less of an issue on high-speed networks. And the reason for that is interface speeds have increased by many orders of magnitudes over the many years since data and packet networking has been a thing. But the packet sizes have stayed essentially fixed. So if you're talking about Ethernet, a 1,500 byte packet, that's been the same from the beginnings of Ethernet all the way up until 100 gig and 400 gig Ethernet. So the serialization delay has gone down quite a bit. So what would have been a 1.23 millisecond delay over a 10 meg Ethernet is now a 0.00123. It becomes unnoticeable at 10 gig Ethernet. But this is still a problem when you run across low-speed interfaces that are out there. And it's an interesting counter-argument to the widespread deployment of jumbo frames. So we actually get some benefit to having small packets relative to the bandwidth size, is that serialization delay becomes less of an issue. So the next thing that comes up is queuing delay. So what do I mean by queuing delay? Queuing is any time the device is holding the packet in memory, waiting for an opportunity to transmit it. So every moment that a router is holding onto a packet without transmitting it, the overall latency is going up. Why do we need queuing in the first place? Well, let's talk about what our concepts of utilization are. So if we've got a 10 gig port and it's doing 5 gigabits per second of traffic, you might say that it's being 50% utilized, but that's actually not correct. So at any given instant, the device is either transmitting, so it's 100% utilized, or it's not transmitting, it's 0% utilized. So what you actually meant when you said 50% utilized was the average utilization over some time period. So you might say 50% utilized over 1 second or 30 seconds or even 5 minutes if you have a really old graphic system. So some level of queuing is necessary for any device to function. And if you doubt that, ask anybody who's ever bought an underbuffered switch. The top of rack switches that are really cheap also tend to have very, very small buffers, and you figure out very quickly that you start dropping packets way ahead of line rate because you need some buffer to handle the normal routing. So here's when queuing is a good thing. You really need it when you have mismatched interface speeds. So remember that packets are actually going to serialize. They're going to arrive faster. So if you have a 100 gig uplink and a 10 gig downlink, that packet is physically going to come across the wire faster on the 100 gig link than it is on the 10. So you're going to need to buffer that packet while you do that transmit. You also see this come up when you have a lot of talkers. So for example, if you've got 40 gig ports that are sending to a very small number of 4 by 10 gig uplink ports, you're going to need more buffering. And technically speaking, queuing always increases throughput. So if you think about it like this, the longer you hold on to that packet, the more opportunity you have to transmit it. So then the question becomes, how long should you hold it? So if it cost you an extra 2 milliseconds to get from 80% utilization to 90% utilization, that might be worth it. But if your application is very latency sensitive, it might not be. So what you typically see is people who are building QoS, they'll build different queue profiles, and they would rather drop a packet early than hold on to it for 10, 20, 30 milliseconds to get it through for a lot of interactive video and voice applications. So when queuing is a bad thing is when the interface becomes more and more full, the amount of time that you need to hold on to it increases exponentially. So like I said, you might be able to successfully deliver that packet, but you had to buffer it for 5,000 milliseconds to do it. That's probably a bad thing. It's probably not what your application wants. So beyond a certain point, it becomes very counterproductive. So yeah, like I said, getting from 98 to 99% utilization, if you had to queue every packet by 5,000 milliseconds to do it, you probably don't want to do it. So as a rule, what tends to be noticeable if you look at it on a 1 second average is most users start to notice a serious problem at around 95% utilization. So you really want to keep it below that level because at that point it's become bad for everyone. And most routers actually have very bad defaults for their interface queues too. So if you search for the term buffer bloat, there's a lot of other presentations that talk about this and what the default value should be and what values you might want to change it to. So here's an example of kind of what that looks like. The actual latency and the actual curve varies depending on the interface speed and the packet type, but this is pretty good example. You see there's like extreme cliff as you get beyond 95%, your queuing effectively becomes infinite as you approach 100. So you want to keep it at 90% or ideally 80% or lower across that average to avoid impacting customers, avoid impacting traffic. The next thing we look at is the propagation delay. So this is effectively, if you think about it, as the time spent on the wire. So simple math, a speed of light in a vacuum is about 300,000 kilometers per second. So if we look at that across fiber, so fiber is actually made of glass and it has a refractive index of 1.48 SMF28. So that means that light propagates across fiber at about 0.67 C. So only about 2/3 the speed of a vacuum or an RF signal. When you transmit it across fiber, it moves at about 200,000 kilometers per second. So 200,000 kilometers per second is 200 kilometers per millisecond. And then if you are looking at it the way that you look at it in Traceroute, you have to divide that in half to account for the round trip time. So a good ballpark is that you should see 1 millisecond of round trip time propagation latency show up per 100 kilometers of fiber that you've spanned. So as an example, if you were to go all the way around the world at the equator, all the way around and then come all the way back on a perfectly straight fiber route, that would take about 400 milliseconds. So it becomes pretty significant to cross large distances. So now we need to identify if the latency is affecting us or not. So how do you determine if that's normal? Well, we start by looking at the location identifiers. So we have some idea of where these things are geographically located, and then we kind of see if it fits the expected profile. So here's an example going from New York City to London. And the total time is about 67.6 milliseconds. So you can go to any Great Circle tool, and you can see that if it was a perfectly straight fiber path, it would be about 3,500 miles, which would be about 56 milliseconds if you were absolutely perfect. We're actually running about 67, so that actually is pretty normal. And if you end up spending any amount of time with the cables, you can look at it and go, that's AC1. You end up knowing what all the cable systems are by their propagation latency. Here's another example. Traffic is coming from AT&T and it's in Washington, D.C. And it goes to a Cogent interface, and that's also in Washington, D.C. So ID being Dulles, Northern Virginia. And you see the latency jump from 8 milliseconds to 228 milliseconds, and you're Washington, D.C. to Washington, D.C. So is that normal? Absolutely not. There's something we need to take a look at. Now we're going to talk about prioritization and rate limiting. So remember when I said at the beginning, traceroute latency is the sum of the time required to get the packet to the hop you're looking at, the time required for that router to drop the packet and to generate an ICMP back to the source, and then the time required for that ICMP to travel all the way back to the source. So number 1 and number 3 come from real network characteristics. These are things that are affecting every packet that you send. But number 2 actually has nothing to do with forwarding conditions. This is something that affects only your traceroute packets. And there's a wide variety of conditions that can cause the routers to either not send the ICMP packet, creating artificial loss, or to be slow in the generation of the ICMP. And this causes artificial latency. So what you really need to understand here is there's a big difference in routers between to it and through it. So most modern routers have these distinct processing paths. So we have what's called the control plane. This is packets that are deliberately being forwarded to the router. So for example, your BGP protocol, your ISIS or your OSPF, your SNMP, or even your CLI access, your telnet and SSH to the device, and any pings. If you were to ping an interface or send any packet to a local IP address of the router, that is going to go to its control plane. Then you have what's called the data plane, and this is for packets that are being forwarded through the router. So inside the data plane, you have a fast path and a slow path. The fast path is something that is hardware accelerated. So you've got ASIC-based forwarding for almost every packet under normal conditions that you want to send. And then you have the slow path. So this is where you go outside of something that can be handled by the ASIC, and it has to be processed by software. So these tend to be exception packets. So for example, IP options, ICMP generation, which is the one we care about. If you do any kind of logging, any kind of exception to the normal rule can cause a packet to be punted to the slow path processor. And the router CPUs that are out there, there are still absolutely deployed in this world 320 to 620 gigabit per second devices that have a 600 megahertz MIPS processor. They're very, very slow. And ICMP generation is not a priority for your router. So this is where you tend to see false things pop up. So on a lot of platforms that are out there, especially legacy platforms, what you have is the slow path data plane and the control plane actually share the exact same resource. So historically, what's happened is, especially if you go look at older iOS devices, they haven't had the best software. They haven't had the best process scheduler. So they're not very precise in how they switch back and forth between process. So what you would see is if you have BGP churn. So for example, you flap a BGP session or you bring up a new session, or you use CLI, so you run a command that takes a lot of resources and generates a lot of output. This can slow the generation of your ICMP TTL exceeds. And this will result in random spikes in traceroute latency that can often be misinterpreted as a network issue. So a really famous example of this was classic Cisco iOS. There's a process called BGP scanner that would run every 60 seconds. It would walk the entire table, just checking to make sure everything was normal. And when it would do this, it would cause these periodic spikes in traceroute performance. So the other thing you have to worry about is rate limits. So remember that ICMP generation through the slow path data plane, there's a lot of reasons that ICMP generation could occur. So for example, it could be a routing loop. If someone sets up a routing loop, that's going to cause a huge flood of TTL0 ICMP generation. So you wouldn't want your device to fall over in the case of a routing loop. You would want it to rate limit its TTL generation and stop when it hits a certain point that it would be problematic. So what tends to happen is there's not really any commercial router with a hardware assisted traceroute function. It falls back to the general purpose CPU. And there's a rate limit on that. And the really tricky part is the rate limits vary wildly, not only by vendor, by platform, by software revision, by different types of hardware revision. So you might have one line card that performs differently than a different line card. And these are often not configurable and not logged. So all it takes is a few users running a tool called MTR that just runs a lot of traceroute over and over. All it takes is a few users to really hit that limit and cause all kinds of drops. So how do you know if it's cosmetic loss or latency, or how do you know if it's a real issue? Well, the trick is if there's an actual forwarding issue, the loss or latency is going to persist across all future packets. So here's an example where we see 0 point some milliseconds, and then we go up to 18 milliseconds to go from DC to Chicago. So that's a normal fiber path, and then we go to 53 milliseconds to go from Chicago to Salt Lake City. So on hop 2, we see this jump to 68 milliseconds. And you might naively look at that and think, well, there's something wrong. There's something congested, or a number of packets occasionally are being queued, or there's some kind of an issue. But it turns out that if you look at hop 3, you see that issue didn't persist. It didn't carry forward into the next hop. Well, that means the issue was cosmetic. That means it was caused by the ICMP generation function of hop 2. So latency spikes in the middle of a traceroute mean absolutely nothing if they don't continue forward. That's first thing to tell people when they look at a traceroute. At worst, it could be the result of an asymmetric path. It could be an asymmetric path combined with multipath. We'll talk more about that in a minute, but more often than not, this is an indication of an artificial rate limit or a prioritization issue. So a good way to test that might be to try something that's not TTL expiring. So for example, ping that router interface that shows up and see if you see the same issue, because you fall into a different kind of a rate limit with that ping directly to our router interface. And some people will allow that in their filters, and some networks won't. So now we're going to talk about asymmetric paths. So remember what I showed you before, Traceroute only shows you the forward path, but at least half of the time that you're seeing is composed of the return path. And it's completely invisible. We don't see it, but that's contributing at least half of, or right about half of the total round trip time that we're looking at. So not only is this path hidden, but there's no guarantee that it is the same path as the forward path. And in fact, in a lot of major networks, it's pretty much a guarantee that it's not going to be the same path. So the only way to confidently analyze a trace route is to have trace routes in both directions. And even then, you can't catch all of the asymmetric paths that are out there, but that does a really good job of eliminating the first level of just blatant, bad, misinterpreted things. So another thing you care about is asymmetric paths and how they hit network boundaries. And why do we care about network boundaries? Because like I said before, that's where the administrative policies change. So here's an example where between DCA, so that's a Washington, D.C. area router, and ASH, so that's Ashburn, Virginia, that's another Washington, D.C. area router, we see the latency jump up to 100 milliseconds. And you look at that and you say, well, what's wrong with this path? So it could be congestion, but congestion tends not to be so precise. You see how it stays almost exactly at 100 milliseconds all the way through. Congestion tends to be a lot more random than that. It could be an asymmetric reverse path. So at this particular boundary, the reverse path policy changes. And where you really see this come into play is in multi-homed networks. So for example, the network that was sending this original packet wasn't single-homed to global crossing, it was multi-homed. So as soon as the packet crossed the border, as soon as it hit Sprint, Sprint now looked at it and said, well, what's the path that I prefer? And it preferred a non-global crossing path. So it preferred a completely different path that we don't see here, and that's the cause of the latency, but it's invisible to us from only this route. So there's some tricks you can use. You can use source addressing to kind of trick around the asymmetric path issue. So in our previous example, let's assume that you're the end user, you're sending that traffic, and you're multi-homed to global crossing and level 3. So obviously global crossing reaches you via global crossing, but in this example, what happened was Sprint came back to you via level 3. So the only way to know what the problem is, like if you had a person on the other end and you could run a reverse trace route and look at it on the other end, that would be great, but assuming you don't have that. So here's some tricks you can use. If you ran a trace route from your network device and you sourced the packet from your side of the global crossing issued /30. So they've issued you, for interconnection purposes, a /30 out of their IP space. That's going to follow their routing policies. So now you see that when you run that trace route sourced from global crossing, it doesn't persist. It tells you something about the reverse path. It tells you that it wasn't coming through global crossing. It was how Sprint reaches you back via level 3. And this kind of trial and error method is what you can use to eliminate a lot of issues. So here's an example of what happens with asymmetric paths with multiple exits. So remember, asymmetric paths can and usually do happen anywhere. Here's an example of a network that interconnects to another network in 3 places. And this is about as simple as it can get, because most networks interconnect, large networks interconnect in dozens and dozens of places all around the world. But so hop 1, we send our packet, and it's going directly across our Washington, D.C. to our Washington, D.C. interconnection. So it's pretty straightforward. We know what it is. Hop 2 goes all the way out to Chicago. So now when it sends it back, it doesn't come back via the same path that it went at all. It comes back via a hot potato to the network, and then back via its return path. And then hop 3, we see that it's changed again because it goes all the way out to San Jose. Now it comes back via the San Jose interconnection. So you typically see this whenever there's a multi-homed, multi-peer network. Most networks use what's called closest exit or hot potato routing. So you're going to see this kind of asymmetric path every time you cross those boundaries. So what happens if the /30 is numbered out of my space? So in the case you're a customer or potentially a peer, you can still benefit from setting source addresses. So consider that you're trying to examine the reverse path of a peer who you have multiple interconnection points with. You can set the traceroute source to your IP address, such as your loopback, and then you can set it to the /30. And what you'll see in a lot of networks that are out there is they carry those /30s. They carry that either in their IGP or in BGP preference higher, such that that will trump the normal interconnection policy. So you can see if the traffic comes back over their backbone versus the interconnection point and the other network's backbone, it can give you different viewpoints. And really what you're trying to do is come at it from many different viewpoints until you eventually find the cause of the problem. Another thing to keep in mind when trace routing from a router is that most routers default to using the source address of the egress interface. So it's where the probe leaves from. And that may or may not be what you want to see. So for some platforms, there is a configuration that you can set. So for example, you can set system default address selection, and then it'll make it source from the loopback always. But you can play around with this. You can set traceroute source, and you can use that to narrow down what you want to see. So now I'm going to talk a little bit about multiple paths and load balancing. So remember, every probe is an independent trial. So if you are using UDP or TCP, what's happening typically is the port, the source and the destination port are being incremented as you move through the network. And they will use this information to identify which probe was which. So what happens in a lot of ECMP, equal cost multipath setups, where you're trying to improve performance of the hash by looking at layer 4 data, is that will force it to take a different path. So here's an example where you see ECMP all the way through. So here's a pair of routers, a BB1 and a BB2 right next to each other, and they go to another pair of routers. They go from London to another pair of routers to another pair of routers. I guess that 8th hop isn't, but it's actually the same device, but it's come over different links. Of these 3 probes, 2 go over one path, 1 goes over the other. So how do you know what you're looking for when you see that? So here's an example of a slightly more complex issue. This is ECMP between 2 parallel but different paths. So one path is Ashburn to New York to Seattle, and the other path is Ashburn to Chicago to Seattle. So it's completely harmless, but if you were to look at that not knowing what's going on, you might think, well, how did the packet go from Ashburn to New York to Chicago to Seattle? And that may or may not be what's actually happening. So the most confusing scenario, the one that trips people up the most, is when you have multiple paths that are of unequal length. So in this example, A, B, C, D, E is your forwarding path, but another equal cost path is from A to X to B. So what you end up having is something that looks like BXB, CBC, DCD, and it looks like at every level that it's jumping back and forth. So when in doubt, the really easy way to work around that is just to send one probe. So for example, your basic Unix implementation, it's going to be -Q1. Junos, for whatever reason, the last time I wrote the slide, lacked that, but you could do it from CLI, from the Unix shell. That gets you one particular path. So you know that all the way through from one to the other, you're looking at one ECMP path. But be aware that it might not be the path over which your actual traffic is forwarding. Let's see. Another issue is MPLS and Traceroute. So many large networks operate an MPLS-based core. It's pretty much a requirement for major networks of some form to run MPLS, to do traffic engineering, to do things that a simple IP network can't. And in a lot of cases, what you'll find is that some of those core networks don't even carry an IP routing table. So that's fine for all the packets that are switched through MPLS, but it presents a real problem when you need to generate ICMP. So how does an MPLS-only router deliver an ICMP message? So one of the solutions that's been implemented is something called ICMP tunneling. So what happens here is if your device ends up generating an ICMP packet for whatever reason, that packet gets put back inside the same LSP that it used, that it was going on originally. And that works for delivering the message, but it makes the traceroute look really weird. So here's an example. Throw out everything that we talked about before about how it comes back from hops 1, 2, 3, 4. And now, as it's generating a packet from router 1 and from router 2 and from router 3 and from router 4, every single one of those things gets carried to router 4 before coming back to you. And if you don't hide the hops inside of MPLS, if you expose the hops, but you use ICMP tunneling, what it does is it makes every hop along the path look and have the same latency as the endpoint. So here's an example of that across AT&T. So we're going from San Francisco through Chicago to New York, but if you were naive and you were just looking at this going, well, how does it jump from 3 milliseconds to 74 milliseconds with it going from Palo Alto to San Francisco? Probably congestion on the interconnection. If you look at it and you notice that the latency stays persistent all the way through, all the way to the end, it's actually a function of AT&T doing ICMP tunneling inside of MPLS, but also exposing their MPLS hops. And some final thoughts. Before you begin any kind of a traceroute analysis, you should always ask for traceroute in both directions. So if someone sent you a traceroute, or if you're sending a traceroute to someone else, see if you can get that reverse path. See if you can take a look at that. And always send your real source and destination IPs. So what tends to happen in a lot of cases is people send only the section in the middle that they think is the problem, and they leave out the source and they leave out the dest. And then when an engineer goes to look at it, they have no way to tell what's actually happening because they've only gotten a snippet of that information. So as a best policy, always ask for traceroute in both directions and the real source and destination IPs. And that is it. Thank you for your time.
Well, Richard, thank you very much. As always, that is one of the 2 most informative tutorials we get at NANOG. I think you know what the other one I'm talking about is. Quickly going to the questions and reading a little between the lines, I'm going to pull some out of the chat. First question from, I'm sorry, I'm going to badly mouth your name, Kanan Catherine Drowerman. Question is ICMP versus UDP versus TCP. When is each probe method recommended?
Well, ultimately, which probe packet you use is whichever one gets delivered to the destination. So the reason for picking UDP is it's historically unfiltered, kind of gets through everything. You can do it with ICMP, and what you'll run across is a lot of networks, especially enterprise networks without people with experience, will do really bad things like, ICMP, that sounds like a security risk, we should block all of it. Or TCP, we have a firewall and that's sitting there and that's going to block everything. But UDP was historically kind of left open by those people. But ultimately, start with, if your traceroute tool lets you do it, start with whatever it sends. And if you suspect that there's something being blocked or filtered, try changing the protocol.
Okay, thank you. And the follow-on questions to that, you probably really just did answers. Are so-called TCP traceroutes better, I think?
Yeah, it's the exact same thing. It's just a packet header that gets through a firewall.
Yeah. And then, of course, there's always our friend, the HTTP traceroute, Twitch. So the next question is, the return path you mentioned is half. Is that the return executes the same process as the outbound? And if so, wouldn't that incorporate the information that a reverse traceroute would?
Let's see if I understand the question correct. What would be really nice, what I would love to see created is a kind of a traceroute, a remote traceroute standard, where people who are willing to put this up can run a host, and it can be a known endpoint. We can connect to it and we can say, I want a traceroute back from you. Obviously, there's a lot of denial of service applications with that, so you would need to almost like a speed test service. I think this will be really helpful for debugging a lot of internet issues. Is if there was a simple, easy, rate limited way where when we do the trace route, we could get the return sent to us as well. But there's really nothing that does that I've seen today. It would be lovely.
Thank you. Two follow-up questions coming from Kanan. First of which is Paris Traceroute the most efficient? What are your thoughts?
It's been a really long time since I've looked at that one. Nothing in particular. I'll say this, there's nothing really efficient or inefficient about it. It's just a matter of how many probes you want to make and what kind of analysis you want to get from the data. There's things that I've done in previous careers. I actually built a massive topology builder by kind of a distributed parallel traceroute system. There's really fancy things that you can do with this. I don't really recommend one tool above another. It's whatever tool you have available, as long as it gives you decent results.
Okay. Thank you. Unfortunately, we're getting a little bit of echo in the system. Questions are coming in fast and furious. How many packets sent per port is ideal? Default is 3. I believe you covered that. Let me flip you to the next one. How is Traceroute running in the data center different? What are things to take care?
Traceroute in the data center. So some examples of things that I've seen. I'll just give an example, random example. Juniper QFX 10K as a platform. When this first came out, they had a little bit of a lag between what you actually sent out of the virtual machine that was running inside the routing engine as they're trying to move to a more kind of modern VM-based system. So it would create these artificial, I want to say it was 10 milliseconds, and artificially add 10 milliseconds to it. And I've seen similar kinds of things out of data center gear because maybe people aren't thinking about, it's much easier to debug a data center. Ultimately, the data center is probably yours. And if it's not, then you probably can't do anything about it unless you're talking to someone who does own it. So they do know the topology. They do know where things are going. They do have access to internal tools and traceroute, reverse DNS, things like that might not be exposed. But always remember to, if you do want to use those kind of data center boxes, make sure that you're testing for what that traceroute application will look like and how end users are going to see it if they try to run traceroute off it.
Okay. Comment that came in on remote traceroute. Remote traceroute, Saku Itai had an idea like that. Perhaps an RFC needs to be drafted. Next question in the stack is traceroute output enough to identify CGNAT properly?
No. I can't think so. That's never one that I've tried to do. Sorry.
Okay. Next question coming in is from one of our PC members. You only mentioned MTR once in the presentation. Not a preferred tool in your opinion?
So MTR is a tool, I think it was Matt's Traceroute or something like that, that just ran Traceroute in a kind of a top fashion, a continuous loop. And what tends to happen is somebody fires this up and looks at it and walks away from their computer. And so this thing is out here sending a few packets per second. That might not be that big a deal, but a few people start doing that across a large enough network, and all of a sudden you are absolutely bumping your hard-coded rate limits on what you will generate for Traceroute. It was kind of notorious for causing those problems when it first came out. I honestly haven't looked at it in a long time, so I'm not sure if they've done anything differently, but that's about it. It's a Traceroute in a top-like interface where you can see continuous refresh.
Does this come under the editorial comment of your management traffic shouldn't exceed your payload for revenue? Okay, next question coming in. Running Traceroute from source to several destinations simultaneously, is it a good idea, or should you run one destination at a time?
So there's two parts of this, right? One is how do you send the packets, and the other is how do you interpret the data. And the way that, one of the problems with the default traceroute, so if you run it and you send a query of 3, and you see one view, one list of hops of 3 separate probes, and in reality, those 3 probes can be completely different. So it would actually be more useful if you had one query all the way through, and then you repeated it, another one query all the way through. And what I would actually want to see if I was to build a better analysis tool would be one that does that again, and then maps out at what point do these change. So here's the view 1 that we got, here's view 2, here's view 3, and here's the differences. I think that would be a more useful view for troubleshooting advanced issues than the traditional traceroute. So that's why I say, if in doubt, go back to one query, look at that one path all the way through, because you have at least some idea that the only thing you're changing about this is the TTL. So ideally, and what should be happening is that should be following the same ECMP, the same flow hash, the same everything. Because you can end up with really complex situations. I've absolutely known people who have done 16-way ECMP of 32 by 10 gig bundles, and so you've got one little thing out of all these different flows that could be causing the problem, and it's really difficult to pin that down. To the other part of the question, which would be how you generate the packets and how you deliver it. There's nothing inherently that stops you from making a map. So the traceroute as a denial of service is actually a potential vector, right? You can send a whole bunch of packets with a TTL that's going to expire at exactly the target that you want and cause excessive CPU use. That's why people have those rate limits. But there's nothing that stops you from making a multi-million packet per second traceroute pinger, so long as you distribute the probes evenly, because there's a lot of hard-coded, I mean, things like 100 packets per second, 1,000 packets per second that you can very easily bump very quickly. And again, it depends on the vendor, the code, the particular line card. So different generations of line cards may have different levels of hard-coded rate limits in there, and a lot of these are not configurable. So it's really more a question of are you going to bump up against those false things because you're sending too much too fast?
Okay. So we probably don't want to crash somebody's network by diagnostics.
Ideally.
It's happening.
Well, ideally what we want is for people to leave those diagnostics open. And a lot of times what you see is people get, oh, well, we want to be extra sure. We want to put lots of rate limits on this. We want to block ICMP, or we want to block everything directly to our /30s. And that cuts out a really valuable diagnostic tool that people on the internet can use to figure out what's going on. So we want to make this as low impact and as beneficial to everyone as we can.
Yeah. Well, editorially speaking, my personal soapbox is people who block ICMP and V6 environments because it just breaks things.
Yep.
Next question. Is there a way to optimize the protocol based on traceroute result when TCP and UDP do not work? The ICMP is chosen intelligently. Interesting thought.
Yeah, it's theoretically possible. I find that one relatively rare. I mean, it's pretty obvious if you're trying to run a tracer out and hey, this isn't getting through. Well, maybe I should try ICMP. You could bake that kind of a basic thing in there, but that's pretty rare.
Okay, we're starting to actually get to the bottom of the question barrel. We do still have some time left. Is there anything you would like to put in as sage advice, wearing your ancient sage hat? At which point we will put in a last call for questions.
my sage advice related to Traceroute. Let's see here. As I said in the very beginning, the thing for me for Traceroute is about using it as a diagnostic tool. And it's when you're running a network, you're talking to someone else who's running a network, you got to figure out what's going on, who to talk to, who to bring the issue to. And there's a lot of situations where people aren't monitoring their own networks, they aren't discovering these things, and they're relying on customers to send that out. So you want to make sure when you're submitting a traceroute, when you're complaining about a traceroute, when you're trying to talk to someone else, be as accurate as possible and include as much information as possible. When people take a snippet of the middle of a traceroute and they don't include the source and they don't include the dest and there's nothing about what's happening, it's almost useless to debug that, unless you're running a very, very broken network and you miss something completely obvious. Include the source, include the dest, include the entire traceroute, if at all possible. I mean, really just the path that it came in and not just the one hop that you think is the problem. And that's about it. The more that we can make that kind of traceroute analysis accurate and helpful, the more we can get every network who has to look at a traceroute issue and then determine if it's a real issue or not, take it seriously, put well-trained people in front of it, and make sure that it gets resolved quickly.
Okay. That was very, very good. As always, is there one? Oh, there's one last question that just came in. You presented once in 2016 and now in 2020. What are your new learnings on Traceroute?
There really hasn't been much. The ironic thing about the Traceroute presentation is if you go look in there, you can see the Traceroutes that I ran in 2014 or whatever this thing was, from the original NANOG and the DR. It's one of those things that doesn't change. It's the same issues affect the same devices in the same way. Really not much has changed.
Yes.
The interface speeds have changed. There's a lot of 100 gig out there. It used to be 110. Some of the interface names are less easy to decode because people have switched to very uninformative names. So, for example, Juniper switched everything to ET, which tells us absolutely nothing except that it's Ethernet. That's about it. It's really the same issues.
Yes, ET, and it still has trouble phoning home. Yeah, I did notice that your trace routes were from a network which has changed names a couple of times since then. Thank you very much for this. It's been most informative as always, and we do look forward to seeing you in person again the next time we see you in person.
Definitely. I miss you guys.
Stay safe. We miss you.
Bye.